Basic Econometric.
Hello and welcome to another lecture on the linear regression model. This time around we're going to focus on the unobserved component U. In particular, we're going to introduce another assumption, the so-called exogeneity assumption, that will restrict the behavior of U. It will turn out that the exogeneity assumption will be crucial for our ability to estimate the linear regression model using data. Let me start out by reminding you of what we already know about the linear regression model. The linear regression model is a way of writing an outcome y as a function of regressors and an unobserved component u. We think of this as representing a production process where outcome y is produced by regressors and unobserved inputs. The unobserved inputs enter the equation through u. So u gives us the combined effect of all unobserved inputs on the production of y. For example, the outcome y could be exam scores on an econometrics exam, and then the regressors could be things like study time, so how many hours did you study, or previous training that you received. And unobserved inputs would, for example, be intrinsic ability. Our ultimate goal is to learn those beta coefficients, in particular the slope coefficients beta 1 through beta k. Once we know these betas, we can compute the causal effect of changing the value of a regressor. For example, the causal effect of increasing your study time. We will learn about these betas using data. And we will obtain this data by drawing individuals from the population and then observing their outcomes and observing their regressor values. We will not be able to have any information on or any data on U because U is unobserved, which means that it is either impossible or just impractical to measure all the observed inputs that feed into U. So no data on U. That actually complicates our analysis. It makes it harder for us to estimate the beta coefficients. So if U is causing problems, why not just get rid of U altogether? Well, the reason is that our linear regression model is supposed to represent what's going on in the real world. And the real world tends to be very complex, with a million things playing a tiny role in pretty much everything. For example, in our study time example, sure, it matters how much you study. And sure, prior training is important. But it also matters how well rested the student is on the day of the exam, what kind of study strategy they chose, and what kind of topics the teacher puts on the exam. So the reason we have U is that without U, the model is just implausible. Let me give you an example of why observing the model only partially is problematic. So here we have again our example population from before. So there's Alice, Ben, and Carl. And obviously Alice does best on the exam. She receives 86 points. And why is that? Well, that's because she has the most amount of prior training. Before she enrolled into the econometrics class, she had already taken 2 statistics classes, and that is very powerful because we know that for every statistics class that you have taken, you receive 15 points on the econometrics exam. And Ben has taken only 1 statistics class, and Carl has no prior training whatsoever. But now let's suppose that we did not have this information on the variable courses. So we would observe only 1 regressor study time. And now, note that the more someone studies, the lower their exam score. Obviously, this is not indicative of any kind of causal relationship, so it is not true that studying more makes you perform worse on the exam. Quite the opposite. In this case, we know what the true model looks like because we've made it up. So we know that study time has actually a marginal effect of positive 2 points. So studying more is good for your exam score. So what's going on here? Well, there is a problem related to the variable courses now being unobserved. Right? So now we have 2 regressors that are unobserved, x2 and x3. So our unobserved component u is equal to the effect of x2, so 15 times x2, and then the effect of unobservability, just like before. So we can compute u for everyone, and now it turns out that the students who study, the more a student studies, the lower is their u. And this kind of systematic relationship between a regressor and the unobserved component is what causes problems. So there is an association between differences in study time and differences in u. So if we see 2 students with different amount of study hours, they will also be different in their unobserved attributes. Now, if these 2 students end up having different exam results, we don't know how to explain that. So it could be driven by their different decisions on how much they wanted to study, or it could be driven by differences in u. The upshot of this is that if we only partially observe the model and don't place any restrictions on u, then it will be impossible for us to learn causal effects. In particular, as the example just illustrated, you can have very annoying behavior that causes correlations to have the opposite signs of the causal relationship. And this is just another reminder that you should never confuse correlation with the indication of a causal relationship. Let's move on to discussing an assumption about u that restricts the behavior of u to a sufficient degree so that we can actually learn causal effects. So intuitively the appropriate assumption will say that we shouldn't be able to predict the value of u by observing the regressors. And the way that we're going to make this assumption precise is by using a mathematical concept that's called a conditional expectation. I'll talk more about what a conditional expectation is in a later lecture. Right now, I want to just give you a rough idea. So a conditional expectation is a prediction that uses information and that exploits this information in an optimal way. So our assumption will be that the conditional expectation of u given the regressors is equal to 0. Let me take that apart for you. So the u here, that's what we're trying to predict. Then the regressors, well, that's the information that we can use. And then the conditional expectation, that's a best prediction, an optimal prediction that exploits the information in the axis in an optimal way. So now our assumption is this best prediction is equal to 0. So 0 is the best prediction. Now what's so special about the 0? Well, the 0 does not depend on the regressors. So what we're saying here is that if you want to predict u given the axis, then actually you will ignore the axis. You will not care about the information that the axis reveal. So the axis, the regressors, are not helpful in making a prediction about u. And this is actually exactly what we wanted to say in the beginning. This kind of assumption is called an exogeneity assumption. So let's add this exogeneity assumption as a second assumption to our set of assumptions about the linear regression model. So this gives us OLS2, an exogeneity assumption. If our linear regression model satisfies the exogeneity assumption, then we say that the regressors are exogenous. So where does this term come from? Well, suppose that the exogeneity assumption is satisfied, then if we draw students randomly, then we will get students with different amounts of study hours, and this variation in study time will be guaranteed to be clean, like clean of contamination by you, in the same way as if we had assigned students different study hours. So in the same way as if we as researchers, as people who are outside of the system that we are studying, who are exogenous to the system, in the same way as if we had just set the values of the regressors. If the regressors are not exogenous, then we say that they are endogenous. And the idea again here is that typically if students decide on, typically students will decide on by themselves how much they want to study. So study times are determined endogenously in the system that we are studying. And obviously this can be a problem, since students might know about their U. For example, they might know that they are very high ability and will do great on the exam regardless of how much they study. So students take into account the U when they choose their study time, and this can endogenously give rise to a relationship, to a systematic relationship between U and the regressors. Now is a very good point to point out that our assumptions are just that, so they are just assumptions, and in particular they may be wrong. And just by me just stating those very confidently, that doesn't make them true. And in fact, whenever you do an empirical analysis, a great part of the work that you have to do is to offer convincing evidence that the assumptions that you're making when you introduce your empirical model, such as a linear regression model, that these assumptions are plausible. So this deserves more attention. So the assumptions may be wrong. Never forget that. Now I want to talk briefly about the random control trial, or RCT. In any empirical analysis that tries to use data to back out causal effects, the weakest point of the analysis will typically be the exogeneity assumption. As long as we are studying economic agents in their natural habitat, the validity of the exogeneity assumption will be a concern. The reason for this is that the regressors themselves are expected to be a result of economic behavior, and thus they might be also endogenous in an econometric sense. The RCT is a research design that makes it relatively easy to justify the exogeneity assumption. So let's assume that instead of studying the economic agents in the natural habitat, we could study them in a somewhat artificial environment where we, as researchers, can manipulate regressors, or that we can assign regressor values to the agents that we are studying. Or in other words, we can control the regressors. If we are able to assign regressor values, then the smartest way to do that is to do so randomly. If we assign regressors randomly, then this will make sure that the regressors cannot predict you. Let me give you an example of an RCT. Suppose that I want to study the effect of taking an econometrics class on labor market outcomes. That is, I want to find out what is the effect of taking an econometrics class on how successful you are in your future job. So the population that I want to study are the prospective employees in the finance industry, so those would be students enrolled in a finance program. All of these students are individuals, and they differ in a lot of ways. For example, they might be different in the intrinsic joy that they derive from doing quantitative work, and probably correlated with that, their ability to do quantitative work. Now, when we write down a linear regression model for labor market outcomes, the ability to do quantitative work would enter through the unobserved component U. So all of these students have different use, and I don't know what they are. I don't observe them. Now it seems reasonable that if students are left to choose what courses they want to take, the students who enjoy quantitative work more will choose more econometric courses. So then later on, when I observe labor market outcomes, if I observe that students who have chosen a lot of econometrics courses are very successful, I don't know if that was just because they are intrinsically have a high intrinsic ability for quantitative work, or if that was because of the many econometrics classes that they took. So this is a typical endogeneity problem. And we will often have these endogeneity problems if we use observational data. Observational data is data that is generated naturally by the economic system that we are studying. But now suppose that there's a university administrator who has agreed with me as a researcher that they will help me manipulate regressive values for the students. And in particular, suppose that there's a course that all students have to take, and that I, the researcher, gets to decide what is taught in this class. So here's what I'm going to do. So I'm going to conduct a random control trial. I'm going to divide all students into 2 groups, and I'm going to do that randomly, so that it's the group assignment is independent of their use. And then the first group, they get to take a real econometrics class, and so typically the group that is exposed to the thing that we are studying is called the treatment group. So this is my treatment group, and the other group, they get to watch a lot of cat videos and talk about internet memes. So nothing useful, really. And so the group that is not exposed to the thing that we're studying, that's typically called the control group. And then once they have taken this class, all the students are moving on, and eventually I will observe their labor market outcomes, and then I can compare labor market outcomes between the groups, and if the group that took the econometrics class does better, then I'm fairly confident that this was causally related to them taking the econometrics class, because it shouldn't be driven by differences in U, because there are no differences in U between the 2 groups by construction. If you want to discuss the validity of the exogeneity assumption, you have to talk about conditional expectations, which at this point may be something that you're not very comfortable with. Fortunately, there's a little trick that you can use if you want to show that the exogeneity assumption is not valid. If you use this trick, you don't have to talk about conditional expectations, you only have to talk about correlations. The trick is based on the following mathematical result. If the conditional expectation of U given the regressors is 0, then this implies that each of the regressors has a 0 covariance with U. In other words, each of the regressors is uncorrelated with the unobserved component U. So that means that in order to show that the exogeneity assumption is invalid, you just have to find one regressor that has either a negative or a positive correlation with U. Then you know that the exogeneity assumption fails. Let's look at this in the context of our example from before. Here it is very obvious that study time x1 and U are negatively correlated. So you see right away that the exogeneity assumption fails. You don't even have to compute a conditional expectation. You can just look at the obvious negative correlation. Now I'm going to talk about an identification result for linear regression. Econometricians say that they can identify the coefficients of the linear regression model if they can write them as a function of the distribution of the observed part of the model. So if they can write the coefficients as a function of the distribution of outcome y and regressors x. Everything I'm going to talk about now presumes that our assumptions all as 1 and all as 2 are met. First, we can write the conditional expectation of y given the regressors as, well, it's just equal to the regression curve. This is implied by the exogeneity assumption. You can prove this equality using by doing mathematical calculations, but we're not going to go through the details. Note, however, this is also very intuitive. Outcome y is made up of the regression curve evaluated at the regressors and u. Now, given the regressors, we predict u to be 0, so it drops out. And if we want to predict the regression curve using knowing the regressors, we just predict the regression curve because it depends only on the regressors. So that is fairly intuitive. Now, about our function of form assumption, all as 1, we actually know what this function m looks like, and we can write it down like so. Now, this is interesting because it tells us that the optimal prediction of y given the regressors follows a linear rule. So in other words, so the the conditional expectation is actually equal to a best linear prediction. So I haven't talked about best linear predictions. I'll have another lecture where I talk more about best linear predictions. But so the most important takeaway from this is that to find the coefficients in the linear regression model, we have to find the coefficients of a best linear prediction. And we know how to do that. In particular, the coefficients of a best linear prediction solve a minimization problem where we minimize a squared criterion or a squared expectation. So here, note what we have done. We have found a way of writing the coefficients, so the coefficients on the left-hand side, and on the right-hand side, the right-hand side depends only on the joint distribution of y and the axis. So if we know the joint distribution of y and the regressors, we can figure out what the coefficients of the linear regression model are. Now, obviously, typically we don't know the joint distribution of y and the axis, but we can estimate it using the method of moments. So this identification result will be the basis of a estimation result that we will cover in a future lecture. There is still a tiny problem with our identification result. Namely, there is no guarantee that the minimization problem on the right-hand side has a unique solution. In other words, there might be multiple combinations of beta values that give rise to the same minimal value on the right-hand side. That is something that we don't like, and so we're going to introduce an additional assumption that rules this out. Assumptions that guarantee the uniqueness of a solution are often called full rank assumptions. So here's a full rank assumption for the linear model. This is a rather technical assumption that usually don't have to worry about, and so I don't want to give you a full-blown formal definition, and I'll just leave it at a rather informal statement. So basically, we want to assume that there's a unique solution of beta coefficients to the minimization problem on the other slide, or we assume that the best linear prediction of y is unique, is associated with a unique set of coefficients. So to understand why this assumption is relevant, it's best to see an example of a scenario where it doesn't hold. So I'm going to present such an example to you in another video. And then I will also discuss why failure of this example, of this assumption can be problematic when we try to interpret the coefficients. I like the term full rank assumptions. Other econometricians use other terms, so often you will find this assumption under the name of the no perfect collinearity assumption. So if you read that in textbook, it means exactly the same thing as our full rank assumption. I've now said everything that I wanted to say in this lecture, so let me conclude by summarizing the main points from the lecture. First, we recognize that if we want to infer causal effects, then we will have to restrict the behavior of u somewhat. it turns that an appropriate restriction comes in the form of the exogeneity assumption. The exogeneity assumption essentially says that we shouldn't, that the regressors should not be predictive of the unobserved component U. The exogeneity assumption is not automatically fulfilled. It will be true or false depending on the economics of the thing that we are studying. It is our job as empirical researchers to offer arguments in favor of its plausibility. If we use observational data, then the regressors will often be themselves will be a result of economic behavior. And in that situation in particular, we have to pay extra attention to the exogeneity assumption. And we have to be sure that there is not a case of econometric endogeneity. Lastly, we discussed an identification result for the coefficients of the linear regression model, and we will, in a future lecture, we will turn this identification result into an estimation strategy.